Hi guys, can you guys hear me?
Yes.
Okay. Okay, I'm going to wait a few more people to join the meeting and then we'll start the meeting. Okay, I'm going to start chapter 20 today. Okay. So in this chapter, we will be learning about electrochemistry. And so what is the study of electrochemistry? Electrochemistry is the study of relationships between electricity and chemical reactions. And we will be learning about how chemical energy is converted to electrical energy, vice versa. So, for example, uh, batteries for your laptop, batteries for your cell phone, batteries for your the electric car, etc. These batteries are operated by conversion between electrical energy and chemical energy. Okay, the chemical reaction that power these batteries are oxidation reduction reaction, or it's called redox reaction. Or this is called redox reaction. Okay, so in the earlier portion of this chapter, we will focus on the oxidation reduction reaction. So we will focus on brushing up the oxidation reduction reaction that we've learned in Gen Chem 1. Okay, um, I know that you've have already learned about the redox reaction in Gen Chem 1, but we will revisit some of those basic concepts in the earlier portion of this chapter. And then towards the later portion of this chapter, we will take a look into the detailed chemical reactions that occur within the batteries, how chemical and electrical energy actually convert to each other. Okay, so let's start by brushing up the oxidation number assigning rules that we learned in Gen Chem 1. Okay. Before we go into the rule, oxidation number is important because this number allows us to keep track of the movement of electrons. Okay, so decreasing in oxidation number indicates gaining electrons, increasing in oxidation number indicates losing electrons. Okay, and here are some of the rules on how to assign oxidation numbers. So the first rule is that any atoms in their elemental form has oxidation number of 0. Okay, so any elements that are by itself, any element that is not combined with any other element will have oxidation number of 0. So it doesn't really matter how many atoms of that element you have, but as long as you only have that single element, the oxidation number will be 0. So the examples would be sodium, okay, will have oxidation number of 0. Chlorine, okay, helium, or oxygen, or octasulfur, okay? It doesn't matter how many atoms, it doesn't matter how many atoms of the element you have within this structure, as long as you only have the single type of element, the oxidation number will be 0, okay? These will all have oxidation number of 0. The second rule is that monoatomic ion have oxidation number equal to its charge, okay? Monoatomic ions are ions that are made up of only one atom. Okay, so for these ions, the oxidation number equals to its ionic charge. So examples would be potassium ion. Okay, nitrogen ion, magnesium ion. Okay, so these will all have oxidation number equal to its charge. Okay, so the oxidation number of potassium will be +1. Okay, oxidation number of this nitrogen ion is going to be -3. Oxidation of this magnesium is going to be +2. Okay, so you need to be able to distinguish between charge of the ion versus oxidation number. Okay, so note that for charge of the ion, charge, you have number in the beginning, number in the front, and charge uh, followed by the number. Okay, so charge after the number. But for oxidation number, you put the sign first, you put the charge first, positive and negative charge first, and then you put the number. Okay, so these are the charge for the ions, these are the oxidation number. So for monoatomic ion, the charge equal to the oxidation numbers. Rule number 3, for fluorine, okay, fluorine, which is halogen, right? Group 7A, sorry, group 7A element for fluorine will always have oxidation number of -1, okay? So for example here, sodium fluoride, for example, the oxidation number of fluorine here will always be -1. Okay. Rule number 4, oxygen usually has oxidation number of -2. Exception is when oxygen is in peroxide, then the oxygen will have charge of -1. Okay, so for example, in here, this oxygen will have oxidation number of -2. Sodium sulfite, oxygen will have oxidation number of oxidation number of -2. But when oxygen is in peroxide, this is an exception. Okay. In this case, oxygen will have oxidation number of -1. Okay, so except for when oxygen is in peroxide, most of the time, all of the time, oxygen will have oxidation number of -2. The next rule is the hydrogen usually has oxidation number of +1 when it's bonded to non-metal, but when it's bonded to metal, it will have oxidation number of -1. Okay, so bonded to metal. Next rule, the sum of oxidation numbers for a neutral compound is 0. Okay. However, you need to add one more sentence to this, is that the sum of polyatomic ion is the charge on the ion. Okay, so for example, neutral compound such as ClF3, the sum of oxidation number of chlorine and fluorine, they should add up to 0. Okay. However, polyatomic ions such as bromate ion, for example, okay, this is a polyatomic ion where two atoms are bonded together that has a net charge that is not 0. Okay, it has a net charge of -1, right? So for this polyatomic ion, the sum of oxidation number equals the overall charge on this ion. Okay, so oxidation number for this polyatomic ion, the sum of oxidation number of this polyatomic ion, it's going to be -1. Okay. And then we need to add another rule. Is that the last rule for ionic compounds that contain in group 1A elements, these elements will always have oxidation number of +1. And ionic compounds containing group 2A elements will always have the oxidation number of +2. Okay, so group 1A element will have oxidation number of +1. Group 2A element will have oxidation number of +2. Here's a summary of how to assign oxidation numbers that I've just discussed in this slide. I have summarized it nicely over here. Okay, if you want to use this to memorize this rule, okay, you can go ahead, or you can reorganize it in the way you like. That's totally fine too. Okay, you should memorize these rules because this information won't be provided for you in the exam. It looks crazy, but once you do few practices, it will get easier and easier. Okay, so let's try this sample exercise from chapter 4. Okay, since this is just a review of what you've already did in chapter 4, I'm going to quickly go over this exercise to just brush up the oxidation number assigning rules. So in this exercise, we need to determine the oxidation number of sulfur in following compounds. Okay, so we're going to start with hydrogen sulfide. Okay, the information we know for sure from the third rule. Okay, the information that we know for sure from third rule is that hydrogen has oxidation number of +1. That's the only thing that we know for sure. Hydrogen has oxidation number +1. Okay. Another information we know from the fourth rule over here is the sum of the oxidation number of this neutral compound has to be 0. Okay, so the oxidation number of this plus this should equal to 0. Okay, so each hydrogen atom has oxidation number of +1. Since we have 2 hydrogen atoms, the oxidation number of 2 hydrogen atoms will be +2. In order for the sum of the oxidation number to be 0, sulfur's oxidation number has to be -2. Okay, so the oxidation number of sulfur is -2 in this compound. For octasulfur, okay, octasulfur, this is an example of element by itself without any other element in the molecular formula. So according to this first rule over here, atoms in their elemental form has oxidation number of 0, so the oxidation number of this octasulfur is going to be 0. Moving on to sulfur dichloride. Okay, the The information we can have from the third rule over here is that halogens, okay, I didn't discuss the halogen rule over here, but halogens, they will usually have oxidation number of -1, okay? Okay, but then if halogen is bonded to oxygen, it will have positive value, okay? So this halogen is not bonded to oxygen, okay? So we will assume that it has a oxidation number of -1. By the way, halogen is group 7A element, okay? So we will assume that it has an oxidation number of -1. Each chlorine atom has oxidation number -1, okay? Since we have two chlorine atoms, the oxidation number of two chlorine atoms are going to be -2. Okay, and also from the fourth rule, we know that the sum of oxidation number of the neutral compound has to be 0. So the sum of oxidation number of this plus this should equal to 0. Okay, so in order for the sum of the oxidation number to be 0, the oxidation number of sulfur has to be +2. Okay, so the oxidation number of sulfur is going to be +2. Let me know if I'm going too fast, okay? Moving on to sodium sulfite. According to the second rule, sodium, sodium is group 1A element. Group 1A, sodium is group 1A element. Okay, so sodium has oxidation number +1. Okay, we have 2 of the sodium atoms, so the oxidation number for this portion is going to be +2. And according to the third rule, oxygen always has the oxidation number of -2, so we know that oxygen will have oxidation number -2. Since we have 3 oxygen atoms with a -2, the oxidation number of O3 is going to be -6. This is also a neutral compound, okay? So the sum of all the oxidation number has to equal to 0, okay? So from sodium, 2 of the sodium, we have +2 oxidation number. 3 of the oxygen, we have -6 oxidation number. So that is +2 minus 6 is -4, okay? So in order for this compound to have 0 oxidation number, sulfur's oxidation number has to be +4. Okay, in this way, +2 plus 4 minus 6 nicely equals to 0. Okay, so the oxidation number of sulfur is going to be +4. For the last compound, okay, sulfate. According to the third rule over here, according to the third rule, we know that oxygen has oxidation number of -2. Okay, oxidation number of -2. Since we have 4 of the oxygen atoms, the oxygen number for this O4 is going to be -8. And according to this fourth rule over here, sum of the oxidation number of polyatomic ion, this is polyatomic ion with charge, right? Sum of the oxidation number of polyatomic ion equals to the charge on the ion. So we know that the oxidation number of this polyatomic ion, the sum of oxidation number of this polyatomic ion is -2. Okay, so then what should be the oxidation number of sulfur in order for the sum to be -2? The only way the sum of the oxidation number of these two atoms equal to -2 is by sulfur having oxidation number of +6. Okay, +6 minus 8 equals to -2. Okay, so the oxidation number of sulfur is going to be, in this compound, is going to be +6. Okay, And here are some of the exercise. If you want to try, okay, you can give it a try after class.
Professor, could you go back to the other slide real quick?
Here?
Yes, I just need to write something down.
Oh, okay.
I'm done, thank you.
Okay, so again, oxidation numbers are important because this number allows us to keep track of which element or compound loses electrons, which one gains electrons. Okay, so if an element increases in oxidation number, okay, the element is called oxidized. If an element decreases in oxidation number, we say the element is reduced. Okay, so in this diagram over here, okay, the zinc oxidation number changed from 0 to +2. Because oxidation number increased, it became positive. Because oxidation number became positive, we say zinc is oxidized. Okay, zinc has lost those negatively charged electrons. That's why it became more positive. Zinc lost electrons. Okay. For hydrogen's oxygen number changed from +1 to 0. So hydrogen's oxidation number okay, so in this case, hydrogen decreased in oxidation number. Hydrogen became negative. Okay, hydrogen is reduced. Hydrogen has gained electrons. Okay, so anything that causes oxidation, we call it oxidizing agent. Okay, anything that cause oxidation, we call it oxidizing agent. So, for example, in the previous example, which one caused the oxidation? The proton, okay? The proton from the hydrochloric acid caused zinc to become oxidized. Zinc is oxidized. This one caused zinc to be oxidized. So that proton is going to be the oxidizing agent for from the previous example. Okay. Anything that causes reduction to occur we call it reducing agent. Okay, so in the previous example, which one caused the reduction? The zinc caused hydrogen to become reduced. Okay, so therefore zinc is the reducing agent. It's the reducing agent. Okay, so the oxidizing agent itself, this will be reduced. Reducing agent itself, the zinc, will be oxidized. Okay, this causes other element to become oxidized. This causes other element to become reduced. Okay, be sure to be able to distinguish the terminology. Okay, this is what I've already explained. Zinc is oxidized. Hydrogen, the proton is reduced. Okay, or this is the oxidizing agent. Okay, why? This is causing zinc to become oxidized. This is the reducing agent. It's causing the proton to become reduced. Let's try a sample exercise. Okay, so identify substances that are oxidized and reduced and and indicate which is the oxidizing agent and which is the reducing agent. Okay, so according, okay, I'm going to bring down this rule sheet. Copy. Okay, so this is the rule. Okay, let's assign the oxidation number using this oxidation number assigning rules. Okay, we're going to start the reactant side first. We're going to start the reactant side first. So cadmium. Cadmium is in its elemental form. According to rule number 1, the oxidation number is going to be 0. Okay. Oxidation number is going to be 0. For nickel dioxide, this is a neutral compound. So we know that the sum of the oxidation number between these two atoms has to be 0. And what do we know for sure? The only thing that we know for sure is the oxidation number of the oxidation number of the oxygen, which is -2, right? Since and we can easily find the oxidation of the nickel using the oxidation number of oxygen. Since each oxygen atom has oxidation number of -2, 2 of the oxygen atom has oxidation number of -4. Okay, so then in order for the total sum of the oxidation number to be 0, nickel's oxidation number has to be +4. positive 4. Okay, moving on to water, we know that hydrogen has oxidation number of positive 1. Okay, and then oxygen has oxidation number of negative 2. We have 2 of the hydrogen, positive 2 of the hydrogen gives oxidation number of positive 2. Positive 2 from hydrogen, negative 2 from oxygen perfectly cancels out, giving oxidation number, sum of oxidation number 0 equal to 0 for a water molecule. So I'm going to write that oxidation number down.
Professor,
Mhm.
so if we're given the coefficient, do we just ignore it?
Yeah,
Okay, thank you.
negative 2 is positive 1, negative 2. And then now we're done for the now that we're done for the reactant side, let's move on to the product side. Okay, let's assign the oxidation number for the product side. The cadmium hydroxide is also a neutral compound. Okay, so we know that the sum of the oxidation number of this compound should also be 0. Sum of the oxidation number should be 0. The oxidation number we know for sure is hydrogen and oxygen, right? So hydrogen and oxygen, hydrogen is positive 1, oxygen is negative 2. Okay, so therefore the oxidation number for this hydroxide is going to be negative 1. Negative 1. Okay, so but we have 2 of the hydroxide. Okay, so then we have oxidation number of negative 2 for this portion. Okay, then in order for this molecule to have oxidation number, sum of oxidation number equal to 0, cadmium's oxidation number has to be positive 2. Okay. I'm actually going to highlight the metals in blue. Okay, positive 2. Oxidation number of oxygen is still negative 2. Hydrogen is still positive 1. Okay. Moving on to nickel hydroxide. This is also a neutral compound, so we know that the sum of oxidation number has to be 0. Okay. Just same as in this situation, the oxidation number of this entire hydroxide is going to be, entire hydroxide portion is going to be negative 1, since we have 2 of the hydroxide is a polyatomic ion. Okay, we have 2 of the hydroxide. This portion gives us oxidation number negative 2. So the nickel's oxidation number has to be positive 2. Okay, so oxidation number of oxygen is still negative 2. Hydrogen is still positive 1. Okay, so okay, so let's take a look at any substances that changed in the oxidation number. The the substances that change in oxidation number are cadmium and nickel only. I'm going to highlight those numbers. Okay, so according to this, cadmium's oxidation number changed from 0 to positive 2. So cadmium has increased in oxidation number. The cadmium's oxidation number became more positive. So cadmium is oxidized. Nickel's oxidation number oxidation number 0 to positive 2. Nickel's oxidation number change from positive 4 to positive 2. Nickel's oxidation number has been reduced. It became less positive. It became more negative. Okay, so nickel is reduced. Okay, so since this is oxidized, since this caused nickel to be reduced, this is a reducing agent. Nickel itself is reduced. Nickel is causing cadmium to become oxidized, so nickel is oxidizing agent. Okay. Reducing agent, oxidizing agent. Okay. Let me know if anybody need more time on this slide. So in next few slides, we will learn how to balance the oxidation reduction reaction. Okay. Balance redox reaction. Balancing a redox reaction can be pretty confusing and complicated. So therefore, we use a method called half reaction method to separate the oxidation and reduction process. So for example, when tin and iron react, tin is oxidized and iron is reduced. Okay, and then through half reaction method, we can separate the oxidation. We can have separate view of the oxidation and reduction process, and it's much easier for us to see which component is oxidized and which component is reduced within the oxidation reaction. Okay, so as you can see, tin is oxidized by losing 2 electrons. Iron is reduced by gaining 2 electrons. Okay, so this is the entire reaction is broken into half, okay, so that we can have separate view of the oxidation process and reduction process. So the rule of thumb here is that the number of electrons lost in the oxidation half reaction must equal to the number of electrons gained in the reduction half reaction. I'm going to write that down. Important. Number of electrons lost in the oxidation half reaction must equal to the number of electrons gained in the reduction half reaction. Okay, so as you can see in this reaction, tin has lost 2 electrons, iron has gained exact same number of electrons. Okay.
Could you go back? Sorry.
Oh, sorry.
Okay, thank you.
So here are steps to balance the redox equation using half reaction method. For step 1, okay, you start by making 2 half reactions. Okay, you separate the oxidation reaction and reduction reaction. For step 2, you balance atoms other than oxygen and hydrogen. Okay, so you balance any other atoms except for oxygen and hydrogen. And then after that, once you balance atoms other than oxygen and hydrogen, then you move on to balancing oxygen and hydrogen. How do you balance them? You balance the oxygen by adding water, okay? And you balance the hydrogen using proton, okay? The next step, for step 3, you balance charges between reactant and product side by adding electrons. For step 4, you multiply common factor to make electrons in half reactions equal. Okay, this is important because again, the number of electrons lost in the half reaction was equal to the number of electrons gained in the other half of reaction, right? For the final step, you add the half reactions together and cancel out anything that appears on both sides of the equation. Let's take a look into let's take a look at the example. Okay, so again, this is a summary of the rule. Okay. We're going to keep this chart throughout the balancing redox reaction process. Okay, so let's try to balance this redox reaction using the method that we just learned. So this is a reaction between permanganate and oxalate, okay, C2O4. Since the very step is to write half reaction, we need to figure out which substance got oxidized, which substance got reduced. Okay, so if we assign the oxidation numbers for manganese, okay, if we assign the oxidation number for manganese, we can see that the oxidation number of manganese changed from +7 to +2. So we know that manganese is reduced. Okay. And then for carbon, the oxidation number changed from +3 to +4. So carbon is oxidized. Okay. So the oxidation half reaction the very first step is to write the half reactions, right? So the oxidation half reaction is going to be this portion, okay, involving carbon. Reduction half reaction is going to be this portion of the reaction, which involves manganese. Okay, so let's balance the oxidation half reaction first. So we're going to balance this oxidation half reaction first. So this is the oxidation half reaction. Okay, again, we're going to keep this chart along. The step after writing half reaction is to balance other atom than hydrogen and oxygen. Okay, so for this oxidation half reaction, we need to balance the carbon first. So any other atom besides oxygen and hydrogen is carbon, right? So let's balance the carbon first. Since the reactant side, the left side has 2 carbon, okay, and the right side has 1 carbon, we're going to add coefficient 2 to the product side in order to balance the number of carbons. And then the next step Okay, so the next step after balancing any other atom than hydrogen and oxygen is now balancing oxygen and hydrogen. Okay, so let's balance the oxygen first. Since oxygen looks like it's balanced, you have 4 oxygen on the left side, 4 oxygen on the right side. So it looks like oxygen is balanced. So we will move on to balancing hydrogen. But since we don't have hydrogen in this equation, in this portion, so we will move on to balancing the charge of both sides of the equation. Okay, since left side has charge of -2, charge of -2. Oh, charge of 2 minus, sorry. Okay, charge is different from oxidation number. Okay, charge of 2 minus. Okay, and then the right side has charge of let's use this. Charge is 2 minus. Okay, this is a neutral compound, it doesn't have any charge, so the charge is 0. Okay, so since left side has charge of 2 minus, right side has charge of 0, to balance the charge between left and right side, we need to add electrons, 2 electrons to the right side. Okay, so by adding 2 electrons on the right side, now we have 2 minus charge for the left side, and you have 2 minus charge for the right side. Now the charge for both sides is now equal to 2 minus. Okay. So now that the oxidation half reaction is balanced, perfectly balanced, we will move on to the reduction half reaction. Okay. So again, the reduction half reaction was this portion of the equation. Okay, so we start by balancing other atoms than hydrogen and oxygen, right? Other atoms besides hydrogen and oxygen. But since manganese is already balanced, we have one manganese, so balanced. So we will move on to balancing oxygen. Okay, since left side has 4 oxygen, right side has none. Okay, so we will add 4 water on the right side so that we have 4 oxygen on the right side. Okay, so we balance oxygen by adding water. Okay, so now the oxygen is balanced, we will move on to balancing hydrogens. Okay, so due to the addition of this 4 water, what happens is that you have increased the number of hydrogen on the right side. Okay, so in order to have equal number of hydrogen on the left side, you need to add 4 times 2, 8 hydrogen or 8 protons on the left side. Okay, that's why you added this. Okay, add water. So you add proton to balance the number of hydrogens. Okay, the next step, now that oxygen and hydrogen are both balanced through adding water, through adding proton, now we will move on to balancing the charges. Okay, so we need to balance the charge. As for the left side, proton has charge of +1. Not +1, sorry. 1 positive. Okay. Charge. Okay. If you have 8 of the protons, so this gives charge of 8 plus instead of 1 plus. Okay. Manganese oxide has total charge of -1. See -1? Okay. You have one of this molecule, so this portion has charge of 1 minus. The total charge for left side is 7 positive. 8 plus plus 1 minus is going to be 7 plus. Let's take a look at the right side. Charge for the right side. Manganese 2 positive has a charge of 2 positive. Okay, water is a neutral compound. There's no charge, right? So the total charge for the right side is going to be 2 plus. To balance the charge on both sides, the only way to balance is by adding electrons, right? So we need to add 5 electrons on the left side. By adding 5 electrons on the left side, the charge on the left side will become 2 positive. Then it will equal to the right side's charge. Okay, so by adding 5 electrons, now the charge on the left side becomes 2 positive. From 7 positive, if you add 5 electrons, it becomes 2 positive. Charge on the right side is 2 positive. So both are, the charges are balanced and they're happy. All right. Now that both oxidation half reaction and reduction half reactions are balanced, this is the oxidation half reaction. This is a reduction half reaction. Okay, since both oxidation half reaction, reduction half reactions, they are both balanced, the final step is to combine these two half reactions together. But before combining, there was a rule of thumb. The number of electrons lost in the oxidation reaction should equal to the electrons gained in the reduction reaction. It looks like you lost 2 electrons in the oxidation process. It looks like you gained 5 electrons in the reduction process. So we need to find a way to make the number of electrons lost and gained same. Okay, so we need to multiply an appropriate integer so that the electron numbers are equal on both oxidation and reduction process. Okay, so if we multiply oxidation reaction by 5, okay, if we multiply the reduction reaction by 2, the number of electrons gained, lost in the oxidation reaction will become 10 electrons. The number of electrons gained in the reduction process is going to be 10 electrons. Okay. So that's what we did here. So we multiplied 5 to the entire equation. Okay. So then you have coefficient of 5, 10, and 10 electrons by multiplying 5. Okay, and then for the reduction half reaction, the coefficients now become 10 electrons, 16 for a proton, 2 for the manganese oxide, and then 2 for the manganese, and then 8 for the water. Okay, so now we see that the number of electrons lost in the oxidation process equal to the reduction process. Everything looks good. We just have to add 2 half reactions together. Okay, so if we add up everything together, we have something like this. So the way to add is you add the reactant side, okay? So you add the reactant side. And then you add up all the products in the product side. Okay, you get something like this. The final step is to eliminate anything that appears on both sides. The only thing that appears on both sides is 10 electrons, okay? So if we eliminate, remove anything that appears on both sides, which is 10 electrons, remove, then we get a final complete balanced equation looks like this, okay? So this is going to be the final completed balanced equation. Okay, so again, you want to verify that equation is balanced by counting the number of atoms and charges on each side of the equation. Let's try a sample exercise. Okay, going to put the copy. Okay, we're going to follow this rule. Okay, let's try to balance this redox reaction. Okay, since the very first step is to write a half reaction, we need to figure out which substance got oxidized and which substance got reduced. Okay, so if we assign the oxidation numbers for chromium, okay, the oxidation number of chromium changed from positive 12 to positive 3. Okay, chromium is reduced. The oxidation number reduced, became less positive. Okay, for chlorine, okay, oxidation number changed from -1 to 0. Okay, so the oxidation number increased, so this is oxidized. So we can now visualize which atom participated in the reduction reaction, which atom participated in the oxidation portion of the reaction. Okay, so the reduction half reaction is Cr2O7 2 minus aqueous Cr3 plus aqueous. This is the reduction half reaction. Oxidation half reaction is this portion of the reaction. Okay. Now let's balance the reduction. Let's balance the reduction half reaction first. Okay. So the step after writing half reaction is to balance. Excuse me. The step after writing half reaction is to balance any other atom besides hydrogen and oxygen, right? So for this reduction half reaction, we need to balance the chromium first. Okay, we're going to balance the reduction. We're going to balance the reduction half reaction first. Okay, so in order to balance the chromium, we need to add coefficient 2 on the right side. Okay, and then the next step is to balance oxygen. Okay, we need to add 7 water on the right side to balance the 7 oxygen on the left side. So I'm going to add water. The next step is to balance hydrogen. Okay, we need to add 14 hydrogen on the left side to balance 14 hydrogens from the right side. So I'm going to add 14 protons. Okay, so this is what I've added so far. This is what I've added so far. And then the next step is to balancing the charge. Okay, we move on to balancing the charge for the equation. As for the left side, charge hydrogen proton has charge of 1 plus. You have 14 proton gives charge of 14 plus. Okay, chromium, the Cr2O7 has charge of -2. Okay, so not -2, 2 minus. So the charge for this molecule is going to be 2 minus. The total net charge for the left side is going to be 12 positive. Okay, so let's take a look at the right side. Chromium 3 plus, oh, is it? Okay, a chromium has a charge of 3 plus. You have 2 of the chromium 3 plus give charge of 6 plus. Okay, and then water is neutral, so has charge of 0. So the total net charge for the right side is going to be 6 positive. Okay, so to balance the charge on both sides, we need to add 6 electrons on the left side, right? Okay, so we need to add 6 electrons on the left side. Okay. So by adding 6 electrons, now the charge on left side is 6 positive instead of the 12 positive, which is equal to the charge on the right side. Okay, so everybody's happy. So now let's move on to balancing the oxidation half reaction. Okay, copy. Okay, this is the oxidation half reaction. And then I'm going to bring the, oops. Bring this rule chart down. Okay. All right. Again, the very first step is to balance any other atom than hydrogen and oxygen. Okay, we have 2 chlorine on the right side, so we're going to put coefficient 2 on the left side. The next step is to balance oxygen, okay, oxygen, and balancing hydrogen, but we don't have any of those. So we will move on to balancing the charge on both sides of the equation. Okay, since the left side has charge of 0. Oh, I'm sorry. Since the left side has charge of 1 minus. Okay, you have 2 of the 1 minus charged chlorine, so this gives us charge of 2 minus. Okay, chlorine is a neutral diatomic molecule. Okay, so we know that the charge on the right side is 0. Okay, in order to balance the charge between left and right side, we need to add 2 electrons on the right side. 2 electrons. Okay, so that's that. And then I'm going to bring this reduction half reaction down. Okay, this is the oxidation half reaction. This is reduction half reaction. Okay, since reduction half reaction has gained 6 electrons, in order to balance the number of electrons lost in the oxidation half reaction, we need to multiply this entire reaction by oxidation half reaction by 3. Okay, multiplied by 3. So in that case, we will have 6 chloride, 3 chlorine gas, plus 6 electrons. Okay, in this way, the number of electrons gained and reduced within the redox reaction, they're equal to each other. Okay, so now the final step is to add both half reactions together and eliminate whatever appears on the both side. Okay, so if we do that, if we add all the products on the reactants on the reactant side, if we add all the products on the product side, we get 14 proton, we have something looks like this. Okay, so this is the perfectly balanced equation. Okay, so
Dr. Lee, can you go back real quick, please?
oh yeah,
Dr. Lee,
uh-huh,
are you particular in which way we order
order.
the molecules or whatever in the equation?
Order of the molecule in the equation. So order, so if you put like chlorine here, if you put like chlorine here and then this Cr2O7 here, are you talking about that kind of order?
Yes. Is that
Oh,
particular?
no, it doesn't matter.
Thank you.
Mhm. Let me know when you're done.
All done. Thank you.
All right, so the sample exercise that we just solved, this was actually in acidic solution. Okay, I'm going to move this. Oops. See, this is what this was in acidic solution. Okay, so the redox reaction can occur in basic solution as well. Okay, so if we want to balance a redox reaction in basic solution, the steps are similar, but it will be a little bit different. Okay, so you should follow the same steps as if you are balancing an acidic redox reaction, but then once the equation is balanced, you should add hydroxide to each side to neutralize the proton. You see how you're adding proton to balance you add proton to balance the hydrogen from the water that you add, right? So you have to add hydroxide to each side to neutralize any proton in the equation to create water instead. Okay, so we're going to solve this. This is going to be a very long exercise, so we're going to solve this during next class. Okay, so the bottom line is that redox reaction can occur in both acidic solution, basic solution. The way to balance redox reaction in basic solution is going to be very, very similar to redox reaction in the acidic solution, but there's going to be a slight difference in the later portion of the balancing of the equation. Okay, so that's the end for today's lecture. I'm going to hang around for another 5-10 minutes just in case anybody else has any questions.